So
Yes.
we are here essentially for automated testing.
Yes, so good morning, everyone. So today in the first lesson, we're going to talk about automated testing, and this will be taught by Thomas Fau from Finland, and from me, Johan Hellsvik, who yesterday I was sitting in Stockholm, and today I'm sitting in Uppsala. So automated testing, what this is about. So we can start by illustrating with some examples here of typical situations. So you have a code, you're working with it, and for over a few months it's stable, and you implement perhaps a new feature B, or you change a feature C. And then all of a sudden, the feature A, which was there in your code for a few years, is not working anymore. And I mean, that can cause a lot of disruption, and you need then to figure out why this happens and how it could be prevented. So I presume that many of you have experienced this at some point, and if this happens, you need to know some good tricks and techniques, and it can be worth to get some good habits with testing because you can save a lot of time with it.
And I can quickly mention here, the B and C can be something that is your code, or actually code from a library like in MATLAB, the different MATLAB version. So suddenly your MATLAB version changes and something in your code doesn't work anymore, as it did in the past. That's, I think, one of the most common situations, at least that I have encountered. That you rely on some library and some library changes suddenly make things not work or work differently.
Yes, indeed. That's a very common situation, actually. So it's very much so that the errors or the source of errors can be in a code itself, or it could be in the environment, or simply in the matching between the code and the environment, because out of the box they might not click together. Okay, so like the other lessons given on Tuesday and yesterday on Wednesday, we will do the examples. We will do them all like in demo mode, and also highlight some of the material which is in the lesson presented as exercises. We will do them then live on the screen. We very much encourage you to then at a later point get back to do some of these exercises yourself. Prerequisites are what you probably are up and running with already. So you need pytest, which is part of Python, and you need to have your Git. Have Git and also your account with GitHub or GitLab. So coming here to the first section, giving here some motivations. So the consequences from software malfunctioning or functioning in a way which is not intended can be of different severity. So a common thing is that something breaks and you need to fix it. Perhaps you need to spend a few hours or half day. That's not the end of the word, obviously. But in the context of scientific research, one of the more severe scenarios would be if you pursue some work on your own or with colleagues, and even you complete it, you communicate it in scientific journals, and perhaps 2 years later you figure out, or someone else figure out that, something here in the code that you used for simulations or calculations within this project, some features were not functioning as intended, and therefore the raw data, perhaps the post-processor data, simply is not correct. And you can find here some some articles here about this. So here is some cases where people even had to retract published work. So I'm just curious. So Thomas, did something like that happen to you, or have you been spared from?
Luckily not, but I would also want to mention that depending on the type of testing you're using, you might not protect yourself against mistakes in your code that you didn't anticipate. Because of depending on the complexity of what you have there might be issues in the code that you just don't realize, even with testing. So it's more, at least to me, the major thing is that you have something you code on, and a bit later, someone asks for changes, and stuff doesn't work as it used to be. That's more what I'm commonly concerned with. That you essentially get suddenly different results from the same functionality, or that some functions just don't do anything anymore. That's more where testing can help you with, or testing kind of prevents.
Yes. I will not do it now, but I've actually myself had some rather, I would say, not so fun experiences where programs that broke, and fortunately this was discovered in, let's say, manuscript review phase. So because it was a referee who requested some additional simulations, and while we were getting on the ball to do these simulations to complement the original results, then we found out, we had done something wrong. And we then had to redo it, and then had to also be transparent in the communicating back to the journal that, okay, we had made a mistake as of a half year ago, we spotted it, we have corrected it, and to the best of our knowledge, this is now, so to say, the sound results. And I would very much encourage transparency in this. So mistakes can happen, and one should not wipe this under the carpet. Also, let's say in communication with journals also. Okay, so how can testing look in practice? So here we have an example. This is in Python code, and we will shortly get to some hands-on exercises on this. So so what do we have here? This is about a temperature conversion from Fahrenheit to Celsius temperature scale. So this here is the function in Python. And Thomas, what do we have here?
So we essentially try to see if what we put into this function gives us the result that we expect the function to give. So we give it one example. Often for relatively basic functions, you might even get a couple of different values that you want to pass in and out, so that you make sure that this is not a hard-coded 37.7777 returning, which would also pass this test, but in more of a general, does this function behave as we expect it to behave? So does it return the right values? And we already see in here we have this absolute smaller than a certain an epsilon kind of assertion. And that's something, especially with floating point numbers, that in tests you will see relatively often, where, floating point numbers are not exact in computers. So you always try to say it has to be almost correct, because correct doesn't work.
Yes. Yes, certainly. And one aspect here is when it comes to numerical computation. So nowadays, I mean, even if you on your local laptop or desktop computer, you often go beyond serial execution of the code, but you have perhaps some kind of threading or some multiple rank computation. And yeah, particularly with threading over CPU cores, then that can very well be, so to say, non-deterministic execution, because you then, if you have, let's say, 8 real numbers and you sum them using 8 physical cores, depending on in which order the summation is made, the rounding errors might come about slightly different.
Yep. Yeah. And what we see here is essentially a so-called unit test. This is testing one atomic unit of the code. So this Fahrenheit to Celsius function does not have any side effects. There is nothing this depends on besides the basic language functions. And that means that we are just testing our code. And as soon as you have function calls from within the function, you start, if it's your own functions that are being called, then this goes into a bit of a different type of testing. Sometimes it's still unit tests, but yeah, it depends a lot on the side effects of your function. And I think that's also what we are going to see next. Where we have.
So here, yeah, you can find, so in this lesson is rather long, so we will not have the chance to cover all of it. So I think we can here and now actually we can come here to a little bit of definitions of what are different kind of tests that we can deal with. So Thomas, you mentioned this, that there is something which is called unit tests.
Yeah. Unit tests essentially are testing that the individual small unit, so an individual function, does what you expect it to do. That under that different kind of inputs that you get always produce what you expect it to produce. That's what a unit test is doing. Then you have integration tests. That's where, yeah, if you have larger parts, if you have one element depending on another element and how they work together, and you test that, you would still write one function that does this test, but you would have essentially an integration test between the two components if they work together as you expect them to work together.
Yeah. Then we have two types here, end-to-end tests, which sort of relates quite a bit to integration tests. But here it's really like the complete program. And if it is, let's say, for a file-based user interface program, you work with input files and the program produces output files, then that lends itself rather naturally for testing, because you then have as your test, or then for end-to-end testing, or essentially a set of input files, and then you have stored then the selected output, complete also with some specification about what would be, let's say, the tolerance for the output.
If there is any.
If there, yeah, exactly. So real numbers are sort of one case, but there can of course be other categories also.
And then you have what's called regression tests, which especially for I think academic work is quite important, because it's essentially that if you do changes, the results don't change. So That would be yeah. I'm using different versions of MATLAB to test that under all the versions of MATLAB. I still get the same results. I'm using different versions of a solver for whatever problems I have, and I'm getting the same, at least conceptual, the same results. I can change. It essentially helps you to be able to change and update code and make code faster and make sure that even if something changed inside, the results that I'm getting out of it are still the same. And if they are not, there should be a good reason why they are not. And maybe you then, well, need to see if the original was correct or if something substantial has changed.
Yes. One thing which is important to keep in mind here with end-to-end tests and regression tests is that, let's say you have engineered your regression tests and you start to deploy them. Let's say you run your program first on a local computer, then you run it on 3 or 4 other servers. And then it's all good for extended time over many months. That tells you then, okay, things are now stable over time. But it's very important to remember also that at some point there's a base case that needs to be sound. And that means at some point early on in the program development, you need then to think like, okay, is the program now doing what it is supposed to do? So yeah, in example for my field of science, computational material science, then it's essentially about doing simulations for differential equations. You get a lot of numbers, and often, let's say, the models that are implemented, they are sort of old, can be 100 years old, 200 years old, and you do have, let's say, for the small problem size, you have the analytical solution, or you can work it out yourself. And that's something which is very useful, because if you can establish, let's say, the analytical solution for some, let's say, a differential equation, or you have it in a textbook or whatever, then you have a base case. And if you then do for that small computation, you do it then with your program, and you get the right results, then you have sort of like a base case. Then probably the typical thing is obviously that on the computer, your program will run something which is bigger and you want to be done faster and so forth. If you can do it a little bit inductively, so that you work from the base case to say like, okay, the machinery in the code is correct here with regard to A and B, and then like, okay, then we can sort of presume that results that are coming out here for C and D have a good, let's say, probability for being correct. So if we can build such things into what then becomes regression tests, that can be of value.
But those can also be unit tests. If you have clear solutions for something, this is exactly what a unit test could also be for. A regression test would be most likely more and now I have a more complex example that I don't have an analytical solution for, and I want that to be stable, even if my code is changing.
Yeah, very good point. You're completely right there. So often, when you look at the components, the units, for them it can often be more tractable to come up with the base case result. So you can establish then that you have a good reference data for your unit tests. So I think we can do a little bit of an interlude here with the discussion on what's easy and hard to test. So I put that question up in the notes. So here towards the end of the collaborative document, so if you could perhaps tell us a little bit of what your experience is on what's easy and what is hard to test?
I would quickly go to the what you should do and what's kind of good practice. I think not every bit of code needs to be tested. There are some basic things that, okay, we trust that they work as they should. There's the thing with code that's really difficult to test, like what's mentioned in the motivation with Jupyter notebooks, and I would there argue that if you can move functional code out of the Jupyter notebook into its own functions, then it's a lot easier to test these bits, to have actual functions that you can then import back into the Jupyter notebook. Then you can test the code.
Yes. Yeah. That's good to be aware of. I mean, Jupyter notebook, which are, depending on how you interact with them, they are, the whole execution flow is depending on your interactive input. So that's a bit more, a bit like a moving target for testing. I think here now in this lesson, we will keep it to like this execution program from the beginning to the end. So we will avoid this.
There's one more thing that to me is a good motivation in writing tests. If you write tests for the functions that you expect users to use, they already have an example of how to run your function. So your tests can, to some extent, also just work for as documentation, essentially. How is this supposed to be used? What kind of things can you do with it? So testing can be integrated in, writing documentation to some extent. And you can reuse things that you use there.
Yeah, indeed. So this is actually a way to be efficient with working on this. Precisely as you said, Thomas, your examples and your input files, if it's a text-based program, and also like documentation and test cases. All of that sort of naturally can be combined and reused as appropriate. So we can briefly highlight here some points before we move over to the next hands-on, so to say. So what are you writing here? So getting an app to a high code coverage can be difficult on a complex and legacy code. Like 95% code coverage, that's very ambitious, probably.
Yeah, the problem with that is, especially if you handle some kind of if you do some exception handling and things, then it becomes really difficult because you essentially need to write tests for every possibility where things can go wrong and how that is then handled. So I completely agree on that.
Yeah, last point here. Generally hard if you do not have modular code. Yeah, certainly. It's very much so.
Which to me is a reason why try to have modular code and don't try to have one huge script that does everything. Try to put it into sub-routines that you can test.
Yeah.
So to some extent, essentially, testing also helps you improving your code quality, in my opinion.
Yeah. Yes. So when you design functions or subroutines, and we'll talk more about that in the second hour. So the design of a function can be guided by its tentative testability. So if you know upfront that, what I'm writing now, it will not be possible to make a unit test for it in any kind of, let's say, straightforward manner, then yeah, okay, perhaps you then have a good reason to reconsider how you are designing that function.
Yep.
And perhaps like it is not a function. That might very well be, let's say, what makes it difficult. Okay, so let's here move over to the next episode here, which is testing locally. And then I think perhaps, Thomas, you would like to take over the screen share? Yeah.
Okay, so essentially, in this exercise, we'll quickly show how to set up a test and how tests work in Python. There are examples in other languages as well, so if your preferred language is one of the others, you can go through those exercises afterwards, but here we'll just show the Python example. So the minimal example that we can create is we can essentially create a folder for our test things. Go in there and then take your favorite editor and take this code. So this code conceptually consists of a function, which is a simple add, and a test function for this, which is very Pythonian because of the untyped language, and you can use integers or floating numbers or whatever and add them, and the plus operator is defined for multiple things. So we actually want this add function to also be able to add strings, and therefore we want to test this for strings. And then in Python, always pytest, which is part of the CodeRefinery environment that you hopefully have installed. It's relatively simple to run these tests by simply calling pytest with the file name that you want to run the tests in or from, and pytest will automatically find every function name that starts with a test underscore. I want to quickly mention that. This is if you use folders, pytest actually looks for all files with test underscore starting. So you could also create two files, one with test underscore example and the test in it, and the other with example, which is called example, and then import the function that you want to test from example into your test. But now let's see what happens if we actually break the test. So if the test doesn't work, and well, one simple option is to just remove or just change the plus into a minus. And if we run the test again, we get a failure here. And this failure essentially tells us that it tried to assert, it tried to assert that -1 is 5, because the result of this at 2, 3 now is -1. Well, 2 minus 3 is -1, and this is not 5. So, yeah, it tells us what went wrong and where what kind of assertion was wrong, and it even tells us where this -1 came from, that it came from this add 2 plus 2 comma 3, because this could be more complex, and then it really helps to see, okay, which side or which part led to a wrong result. Now we have already mentioned that in the introduction. There is a problem that if you have, for example, floating numbers. Oops. and try to do, no, wait. Yeah. Sorry. And try to add those. You might end up with something that's not correct. Or you might end up with some problems. Because if we run this, well, now we see that our addition of 0.1 and 0.2 is not exactly 0.3. And that's what we were talking about with these tolerances earlier. And the problem here is that due to numerics, these are not presented as 0.1 and 0.2, but they have additional information way. I don't know which digit. And you often, for floating numbers, have to do this kind of correction where you take an absolute of, oops, not of this, an absolute of this minus 0.3. No. Wait. Yeah.
Yes.
And define that this is smaller than 1. Smaller than whatever epsilon you want to choose. Don't choose something too large and don't choose something too small.
Yeah, this 1 and then 10 raised to minus 6 is, yeah, I mean, one.
Take something that's appropriate.
It's rather commonly used tolerance, I would say. Like if you have no specific reason for choosing a given tolerance, then this
1 in minus 6 or 1 in minus 9. You might even have, if you have more complex programs, some programs, especially some optimizers, allow you to set tolerances for optimal solutions and things. And if you're setting a tolerance, you should make sure that your assertion for something is also within that tolerance, even if you know the correct result, because you just allowed the program to be not exact. And that might lead to essentially going into the documentation and see what is the default tolerance for this. So if you have an optimization problem and the optimization says, up to 1 to the minus 9, you shouldn't assume that your optimal solution, even if you know what it is exactly that, but could be up to 1 to the minus 9 worse than what you expect. So yeah, each test framework has its own way of collecting the tests. For pytests, it's relatively simple. If you have a function, I can actually quickly show that. How this would be done. So, and if I now just say, please run this on this folder, it will collect from the test example.py will collect test add, which we had defined that, okay, we import the add function from example and then have the test function here. So it will look into all files that have test underscore, collect all functions that start with test underscore and run those. And it does not run the test underscore from example.py because example.py doesn't start with a test underscore. Yeah. Okay. This much for the local testing. Were there any questions, Johan?
Yes, let me check. No, not at this point.
Okay. Then let's go on to automated testing, which is actually really a convenient feature of GitHub, but also GitLab. So to make sure that your code stays correct or stays or that your tests are still running, you could of course always before pushing something run pytest or whatever testing framework you have. But on tendency, at least I tend to forget these kind of things. So having someone else automatically do it for you is really, really convenient. And that's where something called continuous integration or continuous development comes in. So continuous integration essentially makes sure that even if you change something, the tests are still working. This is, of course, under the assumption that the tests haven't changed. So if you change your tests, things can fail, and sometimes you unfortunately have to change tests if the preconditions for the test change.
Yes.
But under normal assumptions, tests should be as static as possible and not change. So in this example, we will essentially run a small example for a continuous integration test with GitHub. And yeah, the assumption is you have your Git login and everything, and we'll begin with just creating a new repository. So this is from your from GitHub. If you click on new repository, you end up in here. We don't want to have a template name, but we want to call it example CI. And want to add a README so that we can make this relatively easily. So let's clone this. And have it in here. So we have a example CI with a README. Okay. Now we want to do exactly this split into functions and test functions here. So we have a file called functions.py, and we want to add this code. And there are some mistakes in here. This is also something that you could call test-driven development. Because to some extent we have tests before we actually do the final the final coding here. So even though our tests are currently not yet active. So, but these are the two tests, the two files that we have. And we need to add them. With a small comment and push it to our remote. So if we run our tests locally, they seem to work because we haven't activated the subtract tests and the Fahrenheit tests yet. Because if we would activate them, they wouldn't work. So to add automated testing, it's actually relatively easy. If we are in our repository and click on Actions, we have this Get Started with GitHub Actions. and we want to use this Python application and configure this Python application. So Johan, did we talk about GitHub Actions in last week? I think so.
Yeah, but I think it's good if you walk it through.
So
the details.
in general, how can I?
We spoke about it yesterday when it comes to deploying documentation with swing stocks.
So in general, a GitHub action is something that is run every time something happens on your branch. So in this case, we tell it that it should do something on push and it should do something on pull requests. And we also I'll just copy that. And we give it certain permissions as to the contents of the repository, and the main permission here is is read permission, so that it can see what's happening in there. And for our action, we also want to give it write access to pull requests, because what we want to do is we want to write something in the end into the pull request that's concerning coverage, because we want to see what our tests actually cover. And to be able to do that, we need to allow it to write into pull requests. Then I'll go over in here. Then it essentially is telling it what. Then it's telling it what kind of basic image to use, so the Ubuntu, and then there are the steps into what it should do. So it uses a checkout action. That's a different action that checks out the repository. Action that sets up Python, and this is where we want to add our instead of just pytest, we also want to add the pytest cuff package, which essentially allows us to add this coverage report in the end. Then it does some linting with Flake, so that our code style is better, or that it at least complains if the code style is not good. And then we want to run pytest, and in pytest we want to create a coverage report, and the coverage report can come in different formats, and we want to have it in an XML format, because the XML format is what is going to be used in the next stage, or in the next step. And we want to create the coverage report for the whole folder. And this create coverage is another action that was implemented, and that is a very simplistic coverage report that's being put into pull requests. Okay, and now how do I get rid of this sidebar here? Seemingly can't, which is really annoying because it covers half of my... Okay. Then we want to commit these changes, and they will be in the .github/workflows folder. And let's call this at CI CD and commit directly to the main branch. Yes. So now this has been added, and now we have an action that says CI CD and builds this Python app. This will take a little bit of time, and at some point, no, this is done. So let's see what this has actually done. Okay, so this has run, set up the job, done the different steps, but it doesn't have didn't create coverage. And the reason why it didn't create coverage is that we restricted this to only create coverages on pull requests because it doesn't for this specific action make sense to create these coverage reports during a push or in this case direct commit, which is essentially a push, because it doesn't have anything to put the coverage report into. So let's see. They have been run, and we can go back here and let's pull what we have. Yeah, git pull origin main is essentially the same as just git pull in this instance because I'm on the main branch, which is tracking the remote or the origins main. Now we want to update our test functions to actually run the test subtraction check. And yeah, because we've noticed that there is an issue with the CI/CD, with the subtraction, we create a new issue. This is not something that you need to do, but this is the assumption that someone else has created this issue because they noticed that something is wrong. Actually, forgot to actually add this. And push it. So, and if we now look into the actions, there's the test for subtract that has been added, and the action is being run again.
So Thomas Ekbrat just mentioned. So there was the question here on in the shared document whether this is type along or pure demo, and what we're doing now is pure demonstrations. So please follow along, and then you can do the exercises on your own later.
Yep. Okay. So let's see. And we actually have this build failed because in the tests indicated that 5 is not the result of or 5 is not -1, and 5 is what comes out of subtract 2 and 3. So seemingly our function is wrong. Well, you might have seen that right in the beginning. So we need to fix this. And add the functions. Actually, how did it? Yeah, this is now a bit the wrong way around, but I forgot to create the branch. So let's. So now I've fixed this issue, and we'll create a pull request to change this. And well, and there are no conflicts, but there is an action that's being run. And let's see if this fixed our problem. So actually, and now we see what this coverage bot does, or this coverage report does. So there is a current status. There were no new files added. Functions.py has a coverage of 75%. And it essentially tells us, okay, this is the coverage of the code that we have at the moment, 75%, and all the tests worked. So that's quite okay. So let's merge this. Let's see if I completely screwed up. No, okay. So I could pull this back to my main branch here. Okay, so what's the next? Next, we do have more tests that we already had. Well, the optimal that we could have is that we get it 100% coverage, but this is not something that you commonly manage to get. But for this simple thing, we can probably try to do this. So we also uncomment this test for the Fahrenheit check, and here it's a bit more complicated. And I'll quickly go over what this is doing. So this is actually the pytest version of having this absolute, and this is probably what you should be doing under normal circumstances. So this is approximating that this number, that the reset from here should be approximately 50, given some tolerance, and in this case, the pytest default tolerance. And there's also a function, an additional, there's an additional statement here, which is sometimes functions are expected to raise errors if they get inputs that are wrong or that are unexpected. And we can even we can test this by having this with pytest test.raises assertion error. If this does not raise the assertion error, then it will fail. So let's see. Let's see what happens if we run pytest here. Okay. So there is definitely an issue with what we have here. And we need to fix our Fahrenheit code. And let's do this now. And now let's see. We had a working Fahrenheit function in the start, in the motivation, because my stuff is it's just the 5 divided by 9.
Yes, indeed, that one definition is working.
So, okay, and if you run the pytest, it's still we have still an issue because it doesn't raise an error. And that's well, actually correct, because it's actually good that that we have this, because we would expect that we can't convert something that's below 0 Kelvin. So a value of minus 600 Celsius, of minus 600 Fahrenheit, just doesn't make any sense. So what's the actual? Let's see. Come on. Da da da. It's in a session. What's the minimum Fahrenheit?
The minimum well-defined number of Fahrenheit.
Something like this.
Yeah, could be. Yes, I never thought about it.
That's 0 Kelvin.
Yes.
At least according to Google.
Mm-hmm.
So,
okay.
And if we test this, that works. And we can, of course, also just, I won't, let's, so edit, put it on, put it to the repository, and then we also see that the issue has been closed because we had a fix in this one pull request. I don't really need further descriptions, but let's see what the coverage report will tell us in a second. I think this is a good finish of the first of this lecture here, or of the first part here. And then, so we have 100% coverage reached, even with a test that, even having a test that uses or that checks for errors being thrown from the function. And I think that's a good time to go for a short break. Or
yes, yeah. Thank you, Thomas. That sounds good. So we will then have a 10-minute break and reconvene at 10 past the full hour. Bye.
Hi, so we are back, and we are back with test design. And I'll hand over to Johan for that.
Thank you, Thomas. So what we will do now will be also be a bit hands-on. We will now be back to, we saw here before the break automated testing, and Thomas was showing how this can be done with GitHub Actions. We could perhaps, there was a few good questions here that we could highlight here. So, yeah, first of all, I mean, you're very welcome to work through these automated testing exercises on your own. And if you have any questions, you can then certainly, as usual, put them here in the collaborative document. How often do you use automated testing?
It depends a lot on the code that I'm working on. The more likely it is to go into some kind of production, the more likely it is to have tests.
So one thing with tests become very popular and is very useful is this, that you set up when you host a Git repository on GitHub, or be it on GitLab, then you can then, if you're the maintainer of that repo, you can enforce so that, I mean, first and foremost, you cannot just commit stuff directly to the main branch. Then, secondly, when you contribute stuff to a feature branch, then that's a very good occasion, a natural occasion to so to say require that you do testing. So probably if you're developing code and you do it locally on your local computer, then you can run the tests with pytest or another framework, and you do it locally. And then when you commit this new code to your feature branch and you make a merge request back to GitHub, then that's a good occasion then to request that, okay, before being able to merge the code, we would like to see all of these tests being passed.
That's definitely something that I've seen being done for larger projects, where you have multiple different contributors and you just want to make sure that you have a high quality code base. And yeah, testing helps in maintaining that high quality code base. Especially.
Yes. And I think this is very important for I mean, indeed, it's very important for larger projects where you simply need to have this a little bit, you need to have a bit of bookkeeping of some kind, because it's not so that you might have, like in smaller settings, perhaps you have the colleague in the same room or in the same corridor, you can just go and ask them and so forth. But if you're 20 person, you sit at 5 different locations, then you need to have some procedures for this. And what is then provided by these services companies, GitHub, GitLab, Bitbucket, and so forth, it's a good platform. So what we are going to talk now about is test design. So this will be a little bit also provide examples of how you can, for a few different types of functions or different code, how you can write tests. And you can see here in the lesson material, and perhaps Thomas, can you check if we have the direct link to this episode in the notes?
Yes, it is.
It is? Okay, great. So we will take it here from the top and work through some of the examples. And yeah, this will be a demo, but I will do it rather slow. So yeah, certainly, if you want, you can do it a little bit type along like-ish, but it's also perfectly fine to get back to it later. So as you can see here, we have language-specific instructions. That means that I mean, the template codes are available in more than one language. And also here we have some instructions on various frameworks for other codes. So we'll get back to that a little bit later, but for the beginning here, we will we'll work a bit, continue to work with Python. So we have here a function. It's called well, simply factorial, and what it's doing is rather clear. It takes one input argument, and that is an integer number, and for this input argument it calculates the factorial. So Thomas, so why is this something that, so to say, is this code that can be tested, or is there some, let's say, pitfall that makes it difficult to test?
this is relatively straightforward because you have a clear function that gets inputs and outputs. You can test for the value error with pytest.raises. You can test multiple different values for it. There is nothing that kind of happens on the side where that you have to take care of because it's all internal. There's not even any. There's one somewhat function called the range, but let's assume that that the Python basic language is correct.
Yes. So I will now shift over to the terminal and then we'll have a look on how this code can be tested. So first I copy the code, so this function definition, and yeah, okay, I already had it here. And also, yeah, actually I also already had here, what is then, let's say, the way how to get started to set up the tests. So we will here use pytest. So yeah, first here's the function, and adding to this we have the import statement, import pytest, and we'll then add some assertions. And in this case here, it's rather clear up front what this could be. So yeah, the factorial of 0 by definition is 1. Then factorial of 1 is also 1, and factorial of 2 is 2. So we have now here, in this case here, 3 assertions in the code, in the test factorial function. So let's see if we go to the terminal, what happens if we execute it. And as usual, we'll then invoke it with pytest. So pytest factorial.py. And yeah, it collected this test item and it came out correctly, and it was very fast.
I would want to add one thing. I dislike one thing about this test, and that is that it doesn't test for the value error that is raised for n smaller than 0.
Yes, very good point. Very good point.
Because that is an essential part of this function, and it should not return something when a value of smaller than 0 gets put in. There's even things where are factorials of non-integer numbers even defined? I don't think so. So this function should make a couple more tests, actually.
Yes.
And that could be caught in a test. Just having a couple more assertions and yeah.
Yes, so that's a good suggestion. So here, so the assertion statements as we have them here are for the out. I mean, this is
for the outputs, yes.
Yeah, for the. I mean, this is for the valid input, and you have the valid outputs. So how could we then do the? So actually, like here, as you can see up here, already in the definition of this code, we do have. I mean, we have this check for the argument built into the method, to the function itself. So in this case here, I mean, we already have a bit of functionality to test for it. So I would say that this is, what we have here, raise value error. That is something which is there's a specific that's error handling. Namely, this that a program. We didn't talk about that earlier, but that is something which is rather important for usability for a program, because you have an intended use case, and if you are making the code, if you're invoking the code with the inputs which are nonsensical, then it's always good to guide the user of the program in the right direction. So in this case here, it will point out that it's not a meaningful thing to try to calculate the factorial for a negative number.
To me, it's something that I think is relatively important if you have these kind of functions, because it's very, very often if you have a function that can just accept anything and gives you something, you end up with wrong results instead of having an arrow thrown at you. And wrong results is something that if you notice that they are wrong, then okay, you can start debugging, but you might even miss that they are wrong. So if a function is by definition only allowed to do certain things, and you expect this function to be used in larger code, it might make sense to make sure that it doesn't get wrong inputs and assert that certain things are not happening, because otherwise you essentially make yourself open to, well, someone has put a wrong number in there, and you now get complete bullocks. And your results suddenly are looking, nonsensical. I have had that in the past, that I had a function that, I expected something to happen, and it didn't, because it had the wrong input parameters. And then it was a lot of work finding, or a lot of time spent finding what exactly went wrong, because I got results, but they were just complete bullocks. They were complete nonsense, and that's something that's really difficult to debug sometimes.
Yeah. You're right about that. I'd say that I think it goes, in many different fields of science, it is so that, the complexity is there, which means that if you would like to cover for all of these scenarios, to provide, let's say, input which is nonsensical, the more you can try to catch, the better. The example I've had here for the factorial is, as simple as it can be. I know some programs where you have, let's say, in the input file, you can have 200 or even 300 different keywords. And perhaps the range for each keyword, if it is about, let's say, numerical values, or sometimes it can be about switches, so that you have, let's say, the program will work in 3, 4, or 5 different modes using different algorithms under the hood. Sometimes, the total number of combinations is, it's a very, very large number. So this is nothing that you can exhaust. Which brings us to this, that for that kind of advanced programs, the user has to be critical to how they are using the program. And well, often is a little bit forgiving here if you're doing modeling as part of research projects, because after all, it's not something which is, let's say, it's not air traffic control or something which is, let's say, mission critical in that sense.
That's entirely true. I would just argue it also helps. It also helps you finding bugs easier. Like this factorial. If you have this in a larger code and the input value for the factorial is something that's being calculated, you could, well, if you end up with a non-integer number, this probably will throw an error because range doesn't allow non-integer values. But if you get something that's smaller than 0 in your computation that you didn't expect, but your value is given, then what you will get as a result from the factorial is 0. I think. Or something that is definitely not what you expected it to be.
Mm-hmm.
Yeah.
Yeah.
Oh, you get 1 actually if you get something negative.
Mm-hmm. So far in the examples that we touch upon here, we were working with numbers, be they integer or be they real. So I think it would be nice here to have a look on something which is working with other types of variables, namely with strings. So we have here an example: design a test for a function that receives 2 strings and returns a number. So this is here in Python. We already have functionality for this implemented. So the name of this function is count word occurrence in string. And we have here 2 input arguments. The first is a string which contains a text. And the second argument is the word. And this is the word for which you would like to count the occurrence within the text. And you can see here in the comment of the code that there's an example of, let's say, example input, and then this string here, 1, 2, 1, 2, 3, 4. If you query for the count of 1, then, I mean, the expected output is 2. So here in Python, this function is, I mean, this functionality is available up front. So we have here the text.split function, which will split the text into the individual words. And we have then a count function. So we can we can count the occurrence of the word, I mean word here in singular, in the words with the object which contains all of the items in the string. So we could type this through. So I start a new source code file here, word occurrence, I call it. And I paste in here the definition of this function. So as we did earlier, we have this function defined here in the Python code. And we can, I mean, this being a smallish thing, we could add the test code within the same text source code file. So what we'll then do is we start defining a test and use the keyword test underscore, and we then have the same name for the function as defined, is only that we had the prefix of test underscore. Yeah, so Thomas, please correct me here if I do some typo.
That looks fine.
Yeah.
Well,
Okay, that's just the header of the test function, and now the keyword is assert, and we then call the function count word occurrence in string. So we need two arguments here. So first we have a mini text AAA. We can take BBB, and we query for one of them. Okay, this is example input of the very simplest form, and as this is an assert, we need them to provide the expected answer. And here, yeah, clearly for this text AAA BBB, we query for AAA, the expected count is 1. Okay, that's one variant. We could then, I copy this line and can make some variations of it. So we could then have, we could add here more occurrences of AAA. Could have CCC. Then query once again for AAA. Yeah, the expected count here should be 2. Okay, I would say that so far this looks a little bit, well, this is nothing difficult in these assert statements so far. But in texts you can have, if it's like normal language, you could have that you have words which are standalone word. Sorry?
Prefixes.
Yeah, exactly. Yeah,
or
you can have
suffixes.
prefixes, or you can have composed words.
Composite words, yeah.
Yeah. So that can make the thing a little bit more complicated. So let's here have another variant, namely to query for just the 5 A's. The text is 5 A's. And here, this is a bit interesting because here I'm not taking this from the lesson material. And, you know, here the suggestion is here, okay, the statement is that the count should be 1.
And I would actually say, no, it should be 0.
Yeah, or it should perhaps be 3. I think it's not at all clear up front.
Yeah.
To me.
Well, to me, 0 or 3 would be acceptable. 1 is actually the completely unacceptable here. 3, I personally, if I want to have a word count, I would assume this is 0 because there is no match. I'm not looking for prefixes, I'm looking for words. But 1 is definitely not what I would what I would want the function to do. But let's see what it does.
Yeah, exactly. Let's see what it does. So keep that one open and wait. Yeah. So pytest word occurrence. Let's see. Okay. That was then another type of error. That was just a coding error. So we need to fix that first. Must have typed wrong here.
Okay.
See?
No, I don't.
No, no.
Admittedly. What was the error?
Just count word.
Count word occurrence in string is not defined. What? Okay, could you go to the terminal again?
Yeah.
So wait, task count word occurrence in string. I don't see it.
No. Okay, but I think we should not get stuck here. So
Yeah.
could I think we could. So this was still. I mean, the interesting thing that we identified here is this that in this case here the function. Functionality here was already available. I mean, within the Python language, we have this split and we have this count. So we're making use of that. And then, as we already had identified here, it's not canonical what would be, let's say, the expected or desired output for having this string 5 A's and then querying for AAA. And as Thomas said, I mean, having it designed so that it should be 0, that's, yeah, I mean, that's one choice you can have for it. Then, I mean, the variant that I mentioned where you could possibly count the occurrence of this string of 3 A's as, I mean, counting it to 3, depending on if you're using the first 3 letters, or letter 2 up until 4, or letter 3 up until 5. So yet again, having like the base case for what is the actual, let's say, by construction, the intended output of a function is obviously important. So we will we'll come to an example here, which is a bit more a delicate situation. So we have here something which is a function to calculate. It's about calculating the temperature of a reactor, and the input argument for this function is a temperature in Celsius. And you can see the comment here. This function, check reactor temperature, is about checking whether the temperature is above a number, max temperature, and then returns a status. And we have here in import statements from reactor, import max temperature. And what this function does, it takes the input argument, temperature in Celsius, and it compares it with these max temperatures. So if the temperature is above, yeah, then the status is 1. And else, if it's not above the max temperature, it's 0. So, okay, the functionality here is perhaps as such reasonable, but there is a problem here. So how could we test this? So
yeah, the problem is essentially that we are getting a value from another class that we don't really have control over, and that could change depending on depending on whatever other factors there are. So we don't know what this max temperature actually is, and we just want to test our functionality, and we don't want to test what the reactor package is doing. We just want to test this check reactor temperature function.
yes, exactly. So this is a simple illustration of a code, a function here, which is, I mean, you can test it only up to a point because you have this external dependency, and could very well be that the external dependency is something that might be, let's say, a moving target or something that you do not have control over. I'd say that sometimes you have, let's say, some constants like parameters in a program. That could be, for instance, you have some conversion factors for, let's say, converting time from hours and minutes to seconds. It's clear that the factor of 60 here is canonical. It's not something that will change. And depending on what program languages you have, you might have like simply this factor of 60. You might have it stored away in a variable which is in scope, so you can use that value when you are in this function.
Another option that I think it might be quite common actually in academia, you have a sensor that gives you values, that has a function that picks a value, and your code needs to pick something from that sensor and use it. But for your test, you don't want to run this on the actual sensor. You don't want to run this on the actual hardware. You want to run this independently. So you have a function that does something, and you want to, just fake that this is actually returning a value from something. That's a very similar situation as well.
Mm-hmm. Mm-hmm. Yeah. Yeah. So I mean, this is all. I mean, you can have situations where this is simply what it is. Nevertheless, if you have, when you, let's say, design new code or augment code with new building blocks, with regard to testing, things become more straightforward if you can use as much as possible pure functions. Because then, in particular, unit tests become much more tractable, because then you can use sort statements of the kind that we have been working with here.
But maybe have a quick look at the solution as to how you can try to get these things in.
Mm-hmm.
And one option here is to use something that's called monkey patching. Monkey patch is another library which essentially allows you to set values or even functions, attributes. In Python, everything essentially is an attribute. So you can replace something by something that is well defined in your environment. So in this case, we are setting the value, the attribute of max temperature to 100. But we could also, uh, if this is a function that gets the value from a sensor, we could replace and it's a function call or originally in your check reactor temperature code. We could set an attribute in the reactor that get temperature is lambda that just returns 10 or something
Yeah,
like this.
yeah, that's really neat functionality. You mentioned it here that this is available as for Python. That's very neat. I'm thinking here about.
There are similar things in other languages as well, but yeah, in Python it's with pytest it's very convenient because what pytest is doing here under the hood is a so-called fixture. Monkey patch is a fixture that is added to pytest and available in any test, and it's essentially by name. So by having this argument monkey patch in the test function, pytest automatically fills in the monkey patch fixture, and then you can use that. And if you have a complex system, you can also define your own fixtures, which can help you in replicating things for multiple different tests. So you only have to write the setup once, because otherwise you would need to write this, this whole attribution setting and whatnot every time. But you could also create your own fixture here that just says that's a temperature fixture or a reactor fixture that essentially replaces all the relevant values in this reactor package by what you want to have for your tests. That's something that you can do. It's not shown here as in the example how exactly, but if you search for pytest and fixtures, that's essentially what this is also doing for monkey patch. But I think we should also go on a bit because we are starting to get towards the end of the time.
Yes. And then I see in the shared document here that someone has caught that the spelling error that I had here in the code, and the typo here was that there's one R missing in occurrence here.
No, not here. In the asserts. The 3 lines below that. In the assert statements.
Okay.
The name of the test function doesn't matter, but in here there's the R's missing. Yeah.
Yeah. Right. You're right. Yeah. Certainly. Yeah. Yes, exactly. I mean, the name here of the test function here.
That doesn't matter.
Yeah, it doesn't matter. But here, this would be here like the canonical name for it because we just had the prefix test underscore, and then the same name. Okay, let's see now if it works better. Oh yeah. Now I also save the file.
Yep. We actually see that. That's also in the comments. We actually see that what Python returns here is 0 and not 1 for the AAA in AAAAA. Because it's not. Because the function splits it and then it's not present anymore.
Yeah. Right. Good. So Thomas, which example do you think we could highlight now? Do you have some favorite?
I would go for the end-to-end test. I wouldn't go into the randomness test for now. I would go to the end-to-end test because it's essentially something that you can also use for regression testing. So this is conceptually. So I think it's design 8.
Yes. So let's move there. Oh yeah, it's about the unique. Yeah, this is also about word counting.
Yes, but it's for the concept to have an end-to-end test here. I think makes a lot of sense in a lot of scientific situations where you have an input, you have an output to whatever code you have, and you want to keep that. And it's the concept is very similar to regression testing, which you very often want to have for scientific code.
Yes. So this is an example of so this how our end-to-end test can be made for in this case here the example is for the unique command. So this is another variant of word count that you will see if a word or a string, if it occurs in the first place, but you would like to filter out the unique occurrences of it.
And if I'm not mistaken here, from what the output at least claims, it's reducing repetitions. It's not actually making looking for unique occurrences, which to me is kind of odd, but okay.
Yes, we can see here, or like a sample input here, which is text, which clearly here is with various lines here, because we have the line breaks here, and obviously it's here repeated. So we have the first line here occurring 5 times, and then this 4 times. This intermission only once, and so forth.
Yeah. So since the aim for this tool is to remove repetitions, what I would start to write my test in is essentially have a couple of files being either files being present that I can use, and then compare the inputs versus outputs. So what do I expect? What do I put in? And what I would do is create a couple of files that are similar to the example input here, actually. Somewhere there's just one line being repeated, and check that, yes, this line is actually being generated again. So reading the output of unique again into a file and then comparing it with something that I have pre-compiled. Since I find it odd that it's not really just giving unique lines, but just removes repetitions. And it also I think is supposed to keep the order. So I would also kind of make sure that yes, it will keep the order, and it will not reorder things. These are the things that I would be trying to check here in a test.
And as I mentioned, so this line here altogether now occurring there and also occurring there, that's somewhat unexpected, because I agree. I would have preferred to see it only written up here,
Yep.
and not here. But again,
At least from the name.
Yeah, from the name, unique, exactly. But like in general, this can often be the case that, well, it can be the case that when some function is written, then there's some freedom in designing what it should do and how it should do it. So I mean, this is like, this was unexpected, but it was intentional, and then your test need to adopt to that. I see here that we have only a few minutes left, and I think here, so we did here intentionally hold on to Python during this lesson. If I scroll back up here to the, well, all the way up to the factorial, sorry. Factorial example, you probably have seen it already, but if not, we have these different tabs here. So Python to the left, but then you can, let's say here you have the function definition here in C++, and there is a template solution for how to test this with frameworks in the respective language. So for C++, you could then, for instance, use the catch2 framework, which is available here. Well, I mean, you need to have it on your computer, and then you can use the include statement here, and then you can get going. And you also have correspondingly, you have, for instance, for Julia R, and also for Fortran. So here you have some template Fortran code, and here in the template solution here, we are, oh, sorry. For this one, the template solution was actually not there. But let's say here for Julia, Julia, without touching upon Julia itself, it is a rather modern language where we do have a framework for testing. It's already there from the beginning, a little bit in analog with that pytest is sort of available for Python. And we could also highlight here that so if we go here to, I mean, the very start of the lesson, and now if I open the menu here, so you have here under the reference heading here, you have quick reference, and here you have a rather extensive listing of unit test frameworks and regression test frameworks and so forth, and they have it then broken down to various languages. So yeah, this is a page that you probably would like to have a look at, and then if you're looking for something for C++ or perhaps for Julia, you can then find you can then you see here some suggestions on tools that you could make use of.
I want to mention one general thing, which is mainly for non-compiled code or non-compiled languages, where what you should keep in mind when doing testing. If you have anything that touches global variables or class variables or similar things, so variables that stay after something is executed, make sure that you reset them after the test, because otherwise you might end up depending on the framework you're using, you might end up with something that was modified in a previous test. Just a general comment here.
Indeed, and I think it goes also for compiled languages that it could be that, I mean, they're executed within a runtime environment that, let's say you have it with some default setting, and if you, let's say, work in a terminal on, could be like a, well, in a way, it doesn't matter if it's on your local computer or if it is on a shared computer, because typically also on the shared computer, you would like to have a grip on your runtime environment. So it's like, for your session, it's your runtime environment. But if you poke around with it, set some environment variables and so forth, then if you have first been working with A and then you go on to work with B, then yeah, you might want to have like a reset after working with A before you get going with B. So we can bring up here the notes to see if, yeah, there's been some interaction here, some questions and some answers.
The how often do you make end-to-end tests in scientific code? The not as often as I should is probably from me. It's in the end, if you have if you have an example of your code, that is an end-to-end test, or you can easily make it into an end-to-end test. You can simply run your example and write a test that when running the code with the input from that example, I would expect the outputs that I just got from this example.
Yes, you're right. So, to my experience is from codes that I'm working with, either as a user or as a developer, then end-to-end tests I'm more acquainted with them and or have, let's say, direct contact with them more commonly. One elegant thing, and there's no time now for us to give to show like that example, but some elegant solutions in some codes where have, let's say, the capacity to do all of this is that, I mean, you have it all. You have like the unit tests, you have the integration tests, and you have also the regression tests. And you have it also part of sort of like the build procedure, like you configure, you make, if it's a compiled language, and then after the make or make install, you make then also like make check. And it runs then through, that could be tens of tests or can even be into the thousands of tests. So now it's 11:05, so it's about time to wrap up, and it will then be the lunch break. And so what do we have after lunch, Thomas?
After lunch, we are going into modular code development. So how do you get your code into a shape that it's more easily reusable? How do you get code out of this is one large script that does everything into pieces that are testable, that are reusable by you or by others, and yeah, similar things.
Yes. So that sounds interesting. So we look forward to that lesson, and let's then conclude this part on testing and have a nice lunch break, all of you.
And see you back in roughly an hour.
Bye bye.